So today I'd like to go over the linked list cycle problem. And the idea behind this one is we want to return a Boolean in our function. And that Boolean is, of course, going to manifest as either true or false. And what we want to do in this case is normally we recognize linked list to be something like this. However, a cycle would be when the last node in the list doesn't point to null. Instead, it reverts back and points on a node that came before it at some point. So we would call this a cycle because if we were to traverse this linked list, we would never reach null. And so it would be a somewhat of an infinity that we would be trapped in because the linked list ends in the sense that the nodes are limited, but it doesn't end in the sense that we reach null at some point. So we want to return true if this is the case and false if it's not the case. So there's something called Floyd's tortoise and hare algorithm, which uses 2 pointers. As you'd probably guess, fast is the hare and slow is the tortoise. The theory states that if there's a cycle in a linked list, and if 2 pointers are moving in a manner that one pointer is moving at double the speed of the other pointer, then there will come a time in the infinity loop where both pointers will refer or point to the same node despite having started at different positions. So what do I mean by that? Well, what I mean by that is that suppose we brought both of these pointers on board and suppose we pointed them at the head of the list. If there is no loop, then fast, which is more naturally the one that will be ahead, and slow will more naturally be the one that will lag behind. If there is no loop, then fast is eventually going to equate to null, right? So we leverage that fact and we say at some point, if there isn't a list or if there isn't a loop, then fast is going to equal null. But if there isn't a list, that's really where we want to get into the logic. So the idea here is that if there isn't a null value, if there is in fact a list, if at some point the list, the end node, reverts back and points to a node that had once came before, the idea is that if both of these nodes, or if both of these pointers rather, are moving in such a manner that fast is moving at double the speed of slow, then at some point in this infinity loop, at some point when they're moving through this infinity, at some point fast and slow will essentially point to the same node at some point. So really what we can say then is that if there is a loop, then fast will equal slow, right? This would mean that there is a loop, and this would mean that there isn't a loop, right? So it seems relatively easy when we talk about it here on the side, but we really want to craft this in such a manner that our algorithm supports all the contingencies that we could perhaps arrive at. So that's really what this paragraph means. If there's a cycle in a linked list, and if 2 pointers are moving in a manner that one pointer is moving at double the speed of the other pointer, then there will come a time in the infinity loop, right? Because if there's a cycle, then this will go on for infinity, where both pointers will refer or point to the same node despite having started at different positions. So hopefully that idea is clear. Now, we've briefly mentioned some of how our code would look here on the side, but let's really flesh this out. We know that we'd want to start both of them from perhaps the head. That's always a safe bet unless we have reason to think otherwise. And I don't think we do at the moment. So we want to move these pointers. We want to move fast, double the speed of slow. Well, what does it mean to move something at double the speed of the other? Well, recall that a pointer has, or a reference, these are node references. these references that we've created, and I'll get more into how we can create them, but these node references have a next property in the sense that, you know, linked lists aren't numerated in the way that arrays are numerated. There's no index ascribed to them. We can't access them as per their index because they don't have one. Had this been arrays, then perhaps this would be much simpler, but that's unfortunately not the case. The only way we can access an element is if we refer, or if we refer to an element using the previous element's next property. So fast has a .next property. Any given node here has a .next property as long as it is being referenced by something. Fast.next, right? So fast, this is what fast is pointing to. So fast.next will be this node, right? And so if fast were here, then fast.next would be this node. If fast were here, then fast.next would be this node. So that's essentially what I mean by saying that as long as there's a reference attached to the node, then you can access the next property to access the next node in line. Now, that would be at regular speed. So saying fast.next is essentially moving something at regular speed. If I were to say fast.next, then I do that again, fast.next, then I do that again, fast.next, that would be regular speed. But what if I did fast.next, .next? Well, on each and every single iteration, I would move fast double the speed. So it's now apparent that I would perhaps want to move slow.next the way I've depicted here, and then fast.next with an extra .next to move them double the speed. But then the question arises that if they both start at the head, how would we actually get them to move? So we've essentially encountered four parts of our code that are indispensable. Fast equals null, fast equals slow, slow.next, and fast.next.next. Now, in order to get that fluid movement, what we would want to do is we would want to use a while null loop, as it's often referred to. And the idea here is that if you want to traverse, we're going to talk about traversing. Traversing a linked list. Remember that in arrays, we would often use a for loop, and we would say array.length, and we would increment I. And then what we would do in the body of this code is we would essentially move we would say let's see here, I'm not able to. We would say nums of I, right? And every time I would essentially, we would say int n equals nums of I. So I would increment each time, and we would be referencing a different element in the array. But in this case, since linked lists aren't numerated the way that arrays are numerated, we really don't have an option. So we use something called a while null loop. The idea here is that we, let's see here, public traversal or public void traverse. I'm going to make a method here. And they usually take the head of the list. And what they do here is they say, okay, while the head is not null, in other words, if we have a pointer, which is the head, and linked lists usually do have pointers that are responsible for the head aspect. While the head is not null, it keeps doing something, right? It keeps moving head one node at a time. So it says while head is not null, it does head equals head.next. So it says head is now what comes after head, which is this guy. So on the second iteration, it would be while head is not null, head is in fact not null, head is equal to head.next. So head now equals the next node in line. And then it does this until eventually it comes to null. Now, you'll often see an implementation of this where they introduce a new node called current, and they set that equal to the head, and then they say while current is not null. The same thing like we did with the head. We would do current equals current dot next. This is, of course, the same implementation, except it's storing head's value or reference value in another node. So how does this fit in the context of our solution? Well, we want to not move just one node, we want to move two at different speeds. So what we can do here is we can say while current is not, or not while current, but what we want to do is we want to first introduce these two references or pointers called slow and fast. So we'll say node slow and node fast. Now you may be confused because when people create nodes, when they create instantiations of the node class, they usually have something like this: node my node equals new node. And the idea behind this is actually creating a new circle. It's creating a new object, but this is just creating a pointer. So there is in fact a difference. So we just want to create not a circle, but just a pointer pointing to what the head reference is pointing to, which we've been given. And both of these, as you probably saw, we want to start them off pointing to the head. So these are just pointers. They're references. They're not actual nodes. So they both start off pointing at the head. And we will use the while null loop. We'll say while fast does not equal the null. And so why I've chosen fast instead of slow is because naturally fast will be ahead of slow. And because I said in order for this to work, fast has to move at double the speed of slow. So naturally fast will be ahead of slow, and fast will reach null before slow ever does. So the idea here is we say, okay, first equals first dot next, because we're moving at double the speed, and slow will equal slow dot next, right? So if there is in fact not a loop, then this will be quickly satisfied. We're going to say while fast is not null, first equals first dot next, slow equals slow dot next. They're going to move at double the speed, but fast is essentially going to reach null and then will break out. So, this is in the case that, in the event that there isn't in fact a cycle, this would have been true. So fast does not equal null. Fast will at some point equal null, and then we'll break out of there and we'll return true. So if we ever broke out, we know that there was a, if we ever broke out, then fast became null, which means there wasn't a cycle. So we're going to say we're going to return false, no cycle. So that's one thing that we'll keep in mind here, is that if we ever break out means no cycle. Okay, and of course you could mix and match this in another way, but for the purpose of our code, if we ever break out, that means there's no cycle. All right. So what we want to do inside is, what if there is a cycle? If there is a cycle, we mentioned that at some point fast will equal slow. So naturally, what we'll do here is we'll say, while this process is happening and while first is moving at double the speed of slow, we'll say if at any given point of time, and we know that this point in time will come if there is a cycle, if fast equals slow, then we'll return true. Right? But if we broke out of this and fast became null at some point, then we'd break out and return false. So this is the basic idea, and I want to show you why this code doesn't run, even though it seems like it does, so that we can better understand the context of the problem and where we may come into errors later on down the road. So we said that we would introduce two nodes. One node would be fast, and we'd initialize that to the head. And the other would be slow, and we'd initialize that to the head. And then we'd say while fast is not null, while fast does not reach the end of the list, essentially what we'll do is, oh, I don't think I was sharing my screen here. But essentially what we would do is, so we have both of our list nodes, this is what they call them in this class definition here, it's list node. So list node fast is head and list node slow is head. So they're both starting at the head. And while fast is not null, while we haven't reached the end, we would essentially just say that fast will equal fast.next.next. We're moving at double the speed. And slow equals slow.next. We're moving at normal speed. And if at any point fast became true, or if this condition became true, then we know that fast reached null, which means that there is in fact a cycle, so we'll return false at the end. So if we ever break out, that means that there wasn't a cycle. But if there was a cycle, then we'll know while we're in the loop. Because if there is a cycle, it's just going to keep on going. So we'll say if first is equal to slow at some point, then we'll just return true. Right. Now this is a solution in theory, right? It almost seems like it should work. And this shouldn't be first here, it should be fast. But this is a solution in theory, it should work. But you'll see that when I submit this, I get a null pointer exception, and I want to talk about that more because I think it's really important to understand. You can see here that on line 19, I get a java.lang null pointer exception. I want to talk about this and flesh this idea out as to why this is the case. So and let me try to do a side-by-side comparison here. Let's see here. Okay. So hopefully this is apparent. And the idea is that what we were doing, I mean, so we have our code, right? I mean, we're looking at our code on the right, and we have a sort of picture diagram on the left. Now, consider that fast is, let's say, here, right? This is fast. Okay, fast is pointing here, and since we know that fast is moving at double the speed of slow, that means slow would perhaps be here. Okay. Now, the thing is that at this point in the code, fast is not null. This is true. Fast is in fact not null. So what we do on this line is we say fast equals fast.next.next. We say fast is equal to fast.next. So now it's null. And then we say dot next again. This is empty space here, right? It doesn't exist. So this is what throws the null pointer exception, right? That is what happens at this point, and that's where we throw the null pointer exception. So one distinction to make here is that if we were here at fast, right, it would have been all right if we did fast.next, right? If at this point we did fast equals fast.next.next, fast would then be null. And that's okay. Fast can maintain a value of null. But then to say fast.next.next, I mean, what would this area be? So that's really the idea here, that when we're at the last node, we're essentially saying fast.next.next, and that throws the null pointer exception. But you'll notice that if fast were here, for instance, right, and then I did fast equals fast.next dot next, this would have been okay, because then I would do fast equals fast dot next dot next. That means fast is null. So that would have been okay. But if fast were here and I do fast dot next, that's empty space. So I could rephrase that to say that, you know, if it were at the last position, if fast were at the last position here, if fast were at the last position, then this code would break. But if fast were at the second to last position, and of course there is no cycle, then it wouldn't break. So in other words, I have to always ensure, that fast dot next is not null, right? Because at this point, I have to ensure that fast dot next is not null. Okay, I have to ensure that fast dot next is not null. I have to ensure that it's a valid value. Because if it is null, then I do fast dot next, then it was null for a second, but then it was nothing. So we got a null pointer exception. So we should alter our code to match this idea. And we want to do that here. So what we're going to say now is we're going to say, okay, well, we're going to keep doing what we were doing before, but we're going to say that, you know, we only want to do fast equals fast dot next if and only if we have a valid value, or if and only if fast, whatever is pointing at fast, does it have a valid value after it? So if fast dot next is not null, then we can move fast at double the speed of slow. Of course, we could have moved slow anyways, and that would work, right? So if fast dot next is not null, then and only then would we want to move them at double the speed. Otherwise, right? Otherwise, we'll just break out, right? We'll break out and we'll return false. And we would essentially break out in order to return false, because if fast.next is null, then there isn't actually a cycle, right? So we would break out and we would return false. So we could now test our code again, having made those adjustments, to see if perhaps we're in a better position. It seems like we are. But what I will mention is that perhaps I think what we could have done alternatively is we could have said, okay, fast is not null. We could have really limited this to fast equals fast.next. So fast.next is not null if there isn't actually a null. If there isn't actually a node after fast, then we could have returned false right here. Return false, right? Because of course, if fast.next is null, then there isn't a loop, right? There's never a null value in a loop, right? So, and then we could say otherwise. Fast equals fast.next, and then slow equals slow.next. Right. Else, just go ahead and do this. And then that I'm positive should reap more or less the same conclusion. And it seems like it gives us a wrong answer. So if fast dot is not null, we're essentially going to return false. And let's see. Right, actually what we should have had is if fast.next is in fact null, then we'll return false. And the opposite would be that fast.next is in fact not null. So we'll go ahead and do this, and then we'll try this in this case, in this instance, and then perhaps that should be all right. So that's the idea here. We really want to remember a takeaway idea, that is, if we're at the end node and we do fast.next, if fast is at the end node and we do fast.next, we won't get a null pointer exception. But if we're at the end node and we do fast.next.next, we'll get a null pointer exception.